Okay, so thanks very much for the introduction. So as Pavna said, I'm a Royal Astronomical Society Fellow at Oxford, and some of the work that I'll be presenting today is with the KITS and LSST desk collaborations, and whenever you see my initials, it means work that I participated in or I led. So this is a talk about cosmology with weak gravitational lensing. And I want to tell you about some of my contributions towards solving some of the challenges that we face with the next generation of experiments, and some new opportunities that also open up as we gather more large-scale structure data. So the outline for this talk is as follows. So I'll talk a little bit about precision cosmology and what that means, but I think it doesn't need much introduction here. The probe that I'll be focusing on for this talk is weak gravitational lensing. So I'll tell you about which observations allow us to test our models of the universe. I'll make a case for cosmology now emerging a little bit with galaxy evolution and galaxy formation, because I think the way that we need to construct more accurate models of the universe for the next generation of surveys is by taking input from galaxy evolution as well. I'll tell you how we implement those models in current pipelines for future experiments, and some of the new opportunities that open up with the data that is coming in the next decade. Okay, so when we think about precision cosmology, we think about the cosmic microwave background. That's justifiably so, because the cosmic microwave background has given us a very precise picture of the composition of the universe. And so we know that 5% of the universe are things that we can see and we can touch, but the rest, the 95% that is missing, is in the form of dark components that are dark matter and dark energy. So 27% of the universe we think is dark matter, and 68% is in the form of dark energy, which is the force that is driving the accelerated expansion of the universe. But what these components are, we're not so sure, and to elucidate their nature, we're going to need further experiments. For this talk, I'll be focusing mostly on experiments that are targeted towards dark energy, and there are a couple of potential options there. Dark energy could be a cosmological constant, as in Einstein's theory. It could be a dynamical field with some equation of state that is parameterized here by this parameter W that connects the pressure to the density of the fluid. That would still be compatible with general relativity, but it could also be the case that there is some modification of gravity that is driving this accelerated expansion of the universe, and we should be able to make this distinction between these different options with upcoming experiments. So how do we do that? So in order to harness the full statistical power of the structure of the universe, we need to identify tracers of that expansion history if we want to learn about the nature of dark energy. And the tracer that I'll be focusing on for this talk is weak gravitational lensing. So we're going to be extracting the information that lies in the large-scale structure of the galaxies that formed after these primordial fluctuations grew by gravity throughout the history of the universe. And we're going to quantify that information in terms of a set of cosmological parameters that describe our model for the universe, that tell us how much matter there is in the universe in the form of dark matter or baryons, how much dark energy there is, what the equation of state of that dark energy is, the current expansion rate of the universe, the amplitude of the fluctuations, and occasionally the sum of the neutrino masses, which we can potentially also constrain with cosmological experiments in the next decade. Okay, so what observations allow us to test these models of the universe? So in this case, I'll be talking about lensing. So lensing is the deviation of the path of photons along the line of sight from a distant galaxy to an observer. So if we're sitting here on Earth, these photons that are coming from this galaxy in the background, instead of coming straight at us, they can be deviated by the presence of massive structures, and their path can change such that the shape that we see for that galaxy is also distorted. And so depending on how matter perturbations grow in the universe as a function of time, which also depends on dark energy, we see a distortion of the shape of the galaxy. The lensing effect also depends on the relative distance between us and the lens and the source. And so by measuring lensing, we can also quantify what we call the distance redshift relation, which is also affected by the dark energy content and the dark energy nature in the universe. To make the most of our data sets, what we do is we try to track this expansion history as a function of time. And so we identify galaxies at different redshifts, and we measure this lensing effect at different redshifts to try to track this evolution of dark energy as a function of time. And occasionally, we also add the cosmic microwave background as an extra redshift bin, because that cosmic microwave background can also be lensed by the whole structure that is intervening between us and that shell of photons. Okay. So what does weak lensing look like? Well, in this case, I took a little bit of an extreme example where we have a nearby cluster of galaxies. So this is a well-known cluster at redshift 0.2, roughly. And you can see that what lensing does is distort the images of galaxies in the background by turning them into these arcs that you see around this central galaxy of the cluster. Okay? So this is a very extreme case of what we call strong lensing. But in reality, strong lensing is very hard to find, so we have to have dedicated algorithms to find strong lens cases in big surveys. But what we can also do is assume that every single galaxy in the universe is somewhat distorted by the whole large-scale structure. And we can pick up those distortions if we look for coherent patterns in those ellipticities of the galaxies. So in this case, I'm not talking about finding arcs anymore, but I'm talking about statistically measuring coherent patterns like this one that you would find around an overdensity, and these are patterns that are of the order of 1%. So you need many, many galaxies in order to recover them. So in practice, how do we do that? So we have a survey of galaxies where we measure their ellipticities, and we have some statistical estimator that weights those ellipticities and gives us a correlation function that is a measure of how correlated the ellipticities are with respect to the separation between the galaxies. And so we take those data points and we make a fit, and this is what is going to give us the cosmological parameters constraints. So there have been several campaigns dedicated to measure weak gravitational lensing. So here we have the Sloan Digital Sky Survey and CFHT lens in the past. Currently active, the Kilodegree Survey, the Dark Energy Survey, and HSC. And upcoming in the next decade, Euclid, LSST, and WFIRST. So I've been involved with some of these in the past, and I'm involved with some of them right now. And let me tell you a little bit about what the current situation is and how it's going to improve over the next decade. So these are current cosmological constraints on the equation of state of dark energy from the Kilodegree Survey. So these are from 2016. There are similar results from Dark Energy Survey and HSC already. And what you see here is that if we think of this parameter W that tells us about the equation of state of dark energy in terms of a constant plus some time varying parameter, then in this parameter space, a universe with a cosmological constant would be sitting here at the center of the crosses. And what we get from the data are these green contours in the case of kids that are 1 sigma and 2 sigma, and you see they are compatible with that cosmological constant scenario. And overlaid here, you also have other data sets and data combinations, but the reality is that the error bars are currently quite large to make any distinction between different theories. But the situation is going to improve, and LSST will be able to shrink the size of those constraints by a factor of 10 to 20. So this is what LSST will be able to do, so I overlaid it more or less to scale. And LSST will not only use gravitational lensing, which is here depicted in the blue contours, but also a combination of different probes that are tracers of this expansion history of the universe. And that combination will be even more powerful, reducing the constraints to this black ellipse over here. So if we see deviations from the crosses when we analyze our LSST data, it could be an indication that dark energy is not a cosmological constant. It could be some kind of dynamical fluid, or it could be a modification of gravity. And the other thing that we do is we combine that information in the gravitational lensing of the galaxies with the lensing of the cosmic microwave background. And the reason we do that is because if both probes, if either probe is affected by a systematic, in the cross correlation of those probes, that systematic effect disappears. So it gives us a robust check that we're doing everything correctly, and we get additional constraints on the cosmological parameters by doing so. And in this case, I'm showing you work from the Euclid survey, where we're constraining the amount of matter in the universe and the amplitude of the perturbations by different means. So in the green, you have the lensing of the galaxies only, and in the black, you have this cross-correlation between the lensing of the galaxies and the cosmic microwave background. And you see that they're both consistent. Okay, so this is another option going forward, the combination of probes and their cross-correlations to obtain cosmological constraints. Okay, but as our error bars shrink in size, we also face new challenges. And those challenges have to do with the way that we model the universe nowadays. And we need more accurate models if we're going to succeed in obtaining parameters for dark energy and other cosmological constraints from our data sets. So I want to tell you about how we develop such models and how we implement them in current survey pipelines. And the two topics that I want to talk to you about are how we model the distribution of matter that sources this lensing effect, and the assumption that galaxies are only, that the shape of the galaxies is only affected by gravitational lensing, which turns out not to be true. So let's start with the first item. So for many years, it has been sufficient in many ways to model the universe as dark matter only. So if you're interested in extracting cosmological information and you wanted a map of the large-scale structure, dark matter comprises 80% of your matter, and so modeling the universe with the dark matter-only simulation seemed to be enough. But it turns out that for cosmological purposes, as our error bars shrink, galaxies are starting to have an impact on our cosmological observable. And so in particular, the supermassive black holes that live at the center of galaxies can have quite a big role in reshaping the distribution of matter around galaxies. And for example, let's say that we compare the case of a universe that's only dark matter to the case of a universe that has galaxies and supermassive black holes in it. So if the true universe is at the center of these crosses, and you're trying to obtain cosmological constraints for this universe, assuming that it's dark matter only, you can get very high bias with respect to the true parameters if you don't model in the effect of the galaxies, okay? So at several sigma, you could end up very highly biased in your constraints for the equation of state of dark energy, for example, if you don't account for this formation of the galaxies and evolution of the galaxies in your model. So in order to gain some information about this effect, I use cosmological simulations like the one that's shown in this figure. So this is horizon AGN, and what you're seeing here is the full width of the box, which is 100 megaparsec over H. In red, you have the stars in the box. In green, the density of the gas, and in blue, the gas temperature. And here you have some examples of the galaxies that are formed in the simulation. So we succeed in forming galaxies with different morphologies. Here are some technical details about the properties of the simulation. The spatial resolution, for example, is 1 kpc, and stellar mass resolution 10 to the 6 solar masses. And we form 150,000 galaxies by redshift 0. By looking at the simulation, we can gauge what the effect of galaxy formation on the distribution of matter is on the large scales. And for that, we have two other simulations that I compare to. So one of them is called Horizon No AGN. So this is very similar, has same volume, same initial conditions, but the only thing that changes is that there's no energy injection from the supermassive black holes in the center of the galaxies to their environment. Okay, so this is a process that we think can have an impact on the distribution of matter, and so this simulation isolates that impact by removing that specific process. And then we have a dark matter, pure dark matter box where no galaxies are formed, so we're just modeling the gravity. And again, it has the same initial conditions, but no galaxy formation at all. So in terms of quantifying the distribution of matter, I'll be using this quantity over here called the power spectrum. So if we take the overdensity field of the universe with respect, the density with respect to the mean -1, and we take the Fourier transform square and take the expectation value of that, that's what's called the power spectrum, and it quantifies the distribution of matter in the box. And this is a quantity that we use in all of our cosmological analysis to model the weak lensing effect. And so if we want to succeed in extracting information from our future surveys on dark energy, we need to know this quantity to within roughly 1%. So this is our requirement. So we need to know this quantity to within that gray bar in these scales of interest to our survey. Okay? So these are large scales and these are small scales in my box. Let's take a look at what the comparison between the different simulation gives us for this quantity. And here it is. So at very large scales, we are within that 1% because the different simulations compare very well. So it seems that galaxies are not having a huge effect on the distribution of matter at very large scales. But at small scales, the picture changes. So if we look at the no AGN simulation where we form galaxies, but there's no AGN energy injection, we have a rise of the power spectrum at small scales. So this is the cooling of the stars, the cooling of the baryons that is driving the dark matter together with them and enhancing the density profiles of halos and forming galaxies in their center. On the other hand, if we look at the full simulation that has this energy injection, we see a decrement of power and then the rise, but at smaller scales. And this decrement of power is due to the active galactic nuclei that are either pushing the gas out of galaxies or preventing it from falling back in by raising its temperature through this energy injection. And so in principle, you could say, well, now I have an idea of what my correct model for the universe should be. It should be somewhere between this line and this line. But then when we compare to what other simulations are doing, we get a large scatter. So these are the other simulations that are available in the literature that have cosmological volumes and for which we could get data for. So this is OWLS, Illustris, the previous version to the existing one, Illustris Next Generation in yellow and red, and EAGLE in purple. And you can see that there's a lot of scatter. And so despite all of these simulations being very successful in reproducing the demographics of galaxies in the universe, in this parameter space, they look slightly different. And different at the level that we should worry about it because it's way beyond that 1% requirement. Okay, so how do we improve on this situation? Before we do that, let me show you a little bit about the redshift evolution of this effect, which is also something that we can look at in the simulations. So here we have the redshift 0 result that I was just showing you for horizon AGN. And we have other curves for the effect at redshift 0.5, 1, and 2. And what we see is that the effect of feedback increases this decrement of power with redshift. So we have more decrement towards low redshift. And also the scales of the problem are changing, right? So we move from having this suppression at a bit larger scale to having it at smaller scales. And the reason that the interpretation that we give to this is that the baryon density inside halos is changing because the AGN are transitioning between a very effective mode of energy injection, which is the quasar mode, to a jet mode at lower redshift, which allows them to reaccrete some of the material that they had lost. So we think that the peak of the AGN effect is somewhere between redshift 1 and 0.5, and then when we go towards redshift 0, the galaxies are not as effective at injecting energy in their surrounding medium, and so they start to reaccrete some of that material back. This is roughly the redshift range between 0 and 3 that we need to model for future surveys. So how do we make progress on solving this problem? Well, I think there are many opportunities here because there are already observations that we're not taking into account when we look at the results of our simulations that we can compare to gauge which one or how much AGN feedback we should have in the universe. And so in this example, what you're seeing is Chandra data from the paper in 2009. So these are 40 X-ray clusters where the fraction of gas has been measured for these clusters. And you can see that the observations lie a bit below the results that we have from our simulation. And so that probably means that our simulation is not injecting as much energy as we need to prevent the gas from falling back into halos, and that the true universe probably has quite a bit more of AGN feedback. But the bottom line is that this kind of information can help us constrain the role of this effect, and in the future one might think of combining this information with the information in cosmological surveys to make a joint model of this effect and cosmology. And so in order to do that, here's an example of a proposed method to do that, where instead of having a hydro simulation, we have a dark matter simulation where we modify the positions of the particles a little bit to account for the effect that the stars and the AGN are having on the distribution of matter. And we do that by using the observational constraints that we have available. And so what you see here is the same plot again at redshift 0, but you have different simulations, which are the black curves, and you have the predictions of the model, which are in red, blue, and green, jointly with some error bars that give you an idea just from the observations and a dark matter only simulation of what the size of the impact of this AGN should be using those observations. And so we're never relying on the hydro simulations as priors, but we use them as a cross-check that the method actually works if we applied it to a given hydro simulation. Okay, so now I want to jump on to the second topic. So any questions up to now?
So you've been sort of implying that AGN feedback is solely responsible for the differences between those different simulations that you were showing, but there are many other differences. So have you shown that it's really the AGN feedback, or are you assuming that? Or?
Right, so it has to be an effect that redistributes the gas. And so we think that there has to be some energy injection into the gas that can move it around. So that could be either AGN feedback or supernova feedback. The supernova feedback effect could be more cumulative, but we think that it doesn't have enough impact or enough energy to really move the gas on such large scales. We don't have additional simulation runs to check that, unfortunately, because these simulations are very expensive. But one could imagine doing some kind of hydro emulator in the future where one could check for the degeneracies between all these parameters. Yes, so that's a very important thing to do in the future, but we don't have that capability right now.
So I thought Illustris did this program of doing all these smaller runs before they did the big run?
Yes, so that's one thing that we're advocating for. So people who run hydro simulations do calibration runs because they're interested in calibrating to different observables. And those are pretty much sitting there untouched, and no one is using them to study that parameter space, as far as I know. And so that's one thing that we would like to do as well.
Please.
Okay, so let me talk about the second assumption, which is the fact that the shapes of the galaxies are just affected by the lensing. So we've known for years that that's not true. So galaxies are aligned in the large-scale structure, potentially due to tidal effects or due to how they formed and evolved in that large-scale structure. But the truth is that if we look at galaxies nowadays, we see that red galaxies are pointing towards each other in the large-scale structure. And we don't know much about the alignment of blue galaxies, but I'll show you why I think we should really worry about it as well. So when we measure a galaxy shape, we're really measuring the lensing contribution to that ellipticity plus some alignment component, so the galaxy can change its ellipticity and orientation according to this alignment component, and then there is some noise on top of that. And so if we're interested in measuring correlations between galaxy shapes, then we won't only have the lensing effect, which is this GG that I show here, but we'll have additional terms coming from the fact that these galaxies are aligned by the same large-scale structure that is creating that lensing effect, okay? So we get additional contributions from these intrinsic alignments. And depending on what redshift regime you're looking at, these contributions could be dominant, or it could be, in the typical case of weak lensing surveys, maybe 10%. So we need to understand them. And they appear across all scales, not just small scales in this case. If we don't understand them well enough, then again, we run the risk of biasing or constraints on dark energy. So if the true universe is here, and we forget to model the intrinsic alignments, then we could end up several sigma away from the true universe. So we need to include them. What do we know about them? We know that elliptical galaxies, which for the purpose of this talk make no distinction between red elliptical and blue disk galaxies. So we're going to have red ellipticals and blue disks, but color and morphology will be the same for me because that's what has been done so far in the literature. So for the purpose of this talk, the red galaxies we know align. There's a model which tells us that the galaxy shape is proportional to the tidal field of the large-scale structure. So you could think of it as the galaxy being stretched by tides of the large-scale structure, or you could think of it as the tidal field giving some, having some influence over the formation history of the galaxy, for example, the accretion directions from where the galaxy got its material, that leaves an imprint in the long term for that galaxy. And there's observational evidence for this. So from the SDSS data, we know that galaxies align to very high significance. So this is a correlation function of the alignment of one red galaxy with respect to the position of another red galaxy. And the fact that these points are different from zero is telling us that indeed they point towards each other. The model is very successful on the linear scales. So that's the blue curve over here. It fits the data very well. And in the nonlinear scales, you start getting into trouble, and you need to improve the situation by making model extensions. They're not very physically well justified, these extensions over here, so this is another thing that we need to improve on in the future, but they kind of work, and they're useful enough for current survey purposes. Another way that we can make progress in quantifying these alignments is by looking at current survey data. So in this joint analysis of the KITS and gamma data sets, so gamma is a spectroscopic sample that we combine with the KITS weak lensing sample. We've split the galaxies in blue and red, and we see that the red galaxies have some alignment, and the blue galaxies have no alignment that we can see in the current observations. And the reason why we made this analysis is that this type of observations brings us closer to the regime of the upcoming experiments, but of course not quite yet there because we don't yet have that full depth that LSST will have, for example. But for the blue galaxies, we're not finding any alignment. We think there's a reason for that. So for the blue galaxies, if they look more like disks, they will have some angular momentum that can be torqued by the large-scale structure, giving them a preferential orientation. But there are reasons to think that that effect is actually quadratic in the tidal field, and so they don't really get that much alignment compared to the red galaxies. But to answer that question of what the blue galaxies are doing, let's look at the simulation again. So we formed realistic galaxies in the simulation, and so why not look at how they align in the simulation and make projections for future surveys? So this is what I did a few years ago. So by splitting the galaxies in disks and ellipticals in the simulation, I looked at whether they aligned, and indeed I found that the red galaxies point towards each other, and the blue galaxies are aligned, and they're pointing tangentially around the centers of density, around the red galaxies. So there is an alignment signal, and that alignment signal, in fact, mimics the weak lensing because it's this tangential effect. But the amplitude of that signal was not large enough to be observed in current surveys, so perhaps in the future we'll be able to observe it with upcoming surveys. We can track the redshift evolution of this effect, and what you see here is that the red galaxies have some alignment early on at redshift 3, but then when you go towards redshift 0, they're increasing that alignment, so they're growing their alignment towards redshift 0. The blue galaxies are more aligned at high redshift, though the alignment signal is much smaller, and then that alignment goes down as we go towards redshift 0. Another reason why we might not have yet seen it. The other thing we can do is we can connect the alignment of the galaxy to the alignment of the dark matter halo that it inhabits, and this could allow us to refine or make give new inputs to semi-analytic models of galaxy formation. And so what you see here is the alignment angle between a galaxy and its host halo, quantified in terms of the major axis of the galaxy and the halo. And what you're seeing is that the galaxies have a very little alignment, so no alignment is here. Very little alignment at low mass, but if they live in very high mass halos, they have a lot of alignment. So this could be related to the merger history of the galaxy, and in fact there's evidence that the more mergers you've had in your history, then the more aligned you become. And this is of course also redshift, it has some redshift evolution, so we'd have to model it different at high or low redshift. Because we have a simulation, we can track the progenitors of the galaxies and ask the question of when these galaxies aligned. And for the ellipticals that we know and love, because we know they're aligned at low redshift, we see that at high redshift, there's very little alignment there in the galaxies, in the progenitors of today's elliptical galaxies, and they grow their alignment with redshift towards redshift 0, and they kind of settled around this redshift range between 0 and 0.5. And these are direct alignments with the tidal field of the large scale structure that we're looking at. And finally, the simulations also allow us to explore the cosmic web, so identified knots, filaments, and walls in the large scale structure, and make predictions with respect to how the galaxies align with respect to those structures. And so what you're seeing here is the alignment of galaxies with respect to filaments in the cosmic web. So each point here is a galaxy in the simulation. And then you see gas filaments, and the density is color-coded by more density in red and less density in yellow and blue. And what we see is that these galaxies have a completely different alignment than the elliptical galaxies. Disks align with their minor axis pointing along the filaments of the large scale structure, while ellipticals flip that alignment and point their minor axis perpendicular to the filament of the large scale structure. And this happens also for walls, and there's a mass transition above which you switch from one alignment mode to the other.
So do you think we can look at this for S0s and distinguish their origin?
Right. So what we could do is this could be mapped to the merger history of the galaxy. So one could presumably take galaxies of different morphologies.
Well,
and then
you don't get to do merger histories for real galaxies.
Right. But you could do. Right. No. But for example, you could imagine training a neural network that will tell you, based on the alignment measurement and the morphology of the galaxy, what the merger history was, for example.
Can't you just measure the alignment history of the alignments of SOs?
Yeah. So the thing is that these alignment signals are very small. So the minute that you start splitting the different samples, it's very hard to get a signal. So you need to have a very large area. Yeah. But yes, we could measure the alignment histories for the different types, and in different environments as well. Okay. So let me tell you about how we integrate models of the large scale structure into libraries that we'll be using for the next generation of surveys. So this is a project that I've co-led for the LSST survey. So here's a LSST being built in Chile. It's actually it's progressed quite a lot since this picture was taken a few months ago. And we're undergoing all the preparations to get ready to analyze the data from the survey, and part of that is building the theory pipeline for LSST. And so I told you that surveys will use a combination of different tracers of the expansion history of the universe to get the cosmological constraints. So these are some of the ones that we'll be using for LSST, so not only weak lensing, but clustering, supernovae, strong lensing, and the CMB. And so we need to have theoretical predictions for all of these that allow us to go from the data that we gather via the models to our constraints on dark energy. And we needed a tool that would be able to do that in a validated way, and that's the tool that I'm talking about today. So this is called the Core Cosmology Library. It's a public product of the collaboration, and you can all download it and use it. What the library does is it takes as input some cosmological parameters, some sample specifications for your survey. So for example, the redshift distribution of galaxies, or some assumptions about what the bias of those galaxies are, And then some systematic parameters like intrinsic alignment amplitude, a model, some parameters for how you're modeling the baryons, and something about the photometric redshift model. And then you pass all that on to the library, which through different methods gives you the predictions for the matter power spectrum that we need, and for the final observables that we will be measuring. So for example, if we are going to be measuring the two-point correlation function, then this matter power spectra is a key component, and we're specifying it by giving all these different inputs to the library. The main reason to create this library is that we wanted to have something that we knew was robust and that was validated to a given numerical accuracy that we liked. And so for each prediction that is incorporated in the library, which corresponds to each probe that we want to model, we've gone through a benchmarking process where there's an accompanying independent public code that we have released, which makes similar predictions and that we compare to. And so in this example, I'm showing you how our correlation functions compare between different codes. And so this is the two-point correlation function of the galaxy ellipticities that we'll be using for lensing. And what you see here is that if this black dashed line is our desired numerical accuracy, our correlations are below that black line. So we went through the effort that for each probe that we're going to need to model, we validated our prescriptions for making the predictions. So this is all publicly available, as I said. The library is written in C and wrapped in Python. You can install it very easily. We're always looking for feedback, so feel free to download it and try it out and let me know if anything goes wrong. We have issues and you can report there, and we're very responsive, so we'll take care of the issue as soon as we can. There are multiple examples of how to use the library, both in C and in Python. So here you have a copy-paste of one of them, where we're calculating distances with CCL, and we're importing it here, and it's specifying some cosmology, and then calculating the distances. So, and there are many cases, including a course MCMC notebook, so you could even try it out for that. All right, so now I want to change topics again and tell you about how some of these challenges that I've been telling you about can actually be turned into opportunities for new cosmological constraints from the next generation of surveys. And in particular, I want to talk about using intrinsic alignments, which we know we can measure, to do cosmology in the future. And so I've been working on this for a while, and we've made several proposals of how to use intrinsic alignments for cosmology, from detecting baryon acoustic oscillations in the alignment signal to primordial gravitational waves from inflation, and also testing different theories of inflation like primordial non-Gaussianity. And so I want to tell you about this one in particular because I think it's the most promising one for future surveys. And so we're going to be focusing on extracting information of the early universe from these alignments of the galaxies with the large-scale structure. So if we have a universe that's Gaussian, then the correlation function of the density field with the shape of a galaxy will be given by this term over here. So this is a simple linear term that relates the shape of a galaxy to the tidal field via some bias parameter that's called here B1i. Okay? So this is the simple model that we know works for elliptical galaxies in, for example, the Sloan Digital Sky survey today and many other surveys as well. Now, if the universe is non-Gaussian, which can happen in different models of inflation, like this one's listed here, then you can get an additional contribution to that alignment. And what that does is, if you're familiar with the FNL scenario where the clustering of galaxies can be enhanced by the presence of a non-Gaussianity, well, in this case, the shapes of galaxies, their correlations of their intrinsic shapes can be enhanced as well by the presence of different types of non-Gaussianities. So this gives a complementary non-Gaussianity probe for the large-scale structure to the clustering of galaxies that aims to constrain FNL. So how would we do that? So let's say that we have these parameters for a model of inflation. So A0 is related to FNL, so the scale-dependent clustering bias. It's actually for FNL, in case you're interested. And then there's this parameter that has to do with inflationary models that change the response of a galaxy to the tidal field. So these are models that have some anisotropy early on in inflation that can propagate to the shape of the galaxy today. And so let's take a look at how LSST is expected to do when measuring shapes of galaxies and measuring this alignment signal. And here we have the constraints that we expect to get, which are 1 sigma, 2 sigma, 3 sigma. And this is 4FNL, and this is the new parameter, the one that we can constrain with intrinsic alignments. And this is okay, but it's more or less at the same level of the constraints that you would get from the bispectrum of the CMB, so it's not fully competitive. So here's a proposal to do that, to make that a bit more competitive, which is the following. Imagine that you have a galaxy. You could, if the galaxy was well resolved, and this is an example from the simulations, you could measure the shape of a galaxy at different radii. So not just one shape as we do for weak lensing, but really the isophoto variations of that shape of the galaxy. And so for example, here we have 2 shapes, one in the purple, measured from the enclosed light in the purple circle, and then one measured from the enclosed light by the white ellipse. And those shapes don't necessarily respond to tides of the large-scale structure in the same way. And in fact, there's evidence both from these observations and from the simulations that the outskirts of a galaxy tend to have more alignment. And this is because those outskirts are less gravitationally bound, which means that they can be more sensitive to tides and they can be more elongated or more sensitive to the last merger that a galaxy had. And so we could use that to our advantage. So the same way that in clustering, there has been a proposal to combine clustering samples that have different biases. This is the same proposal, a multi-tracer approach, where you combine different samples that have different shape biases. And if you do that, then you go from here, which is the original constraint that, that we had, the original forecast that we had for how well we were expecting to do, to there. And now you really become competitive with the CMB, and you're about 50% better than the CMB in constraining these parameters. And so I think this is a promising way for learning about models of inflation in the next decade.
That's just using 2 different radii?
Right, that's just using 2 different shapes, yeah. And you could define them, in fact, you could define them pretty much anywhere you want it, because we're still marginalizing over the parameter of the amplitude of the alignment. Okay, so to summarize, I think we have exciting prospects for weak lensing and combined tracers cosmology in the next decade. They come at a price, the price that we need to improve our models of the universe, and that means understanding some of the astrophysical effects that we didn't care about before for cosmology, but that we need to introduce now, and we need to discuss with our galaxy evolution colleagues how to do that in a coherent way. So this is not only an opportunity to learn about galaxy evolution, but also early universe through the shapes of galaxies. So what does the future look like? So all of these improvements in the models need to be passed on to our pipelines for the upcoming experiments like LSST. We get our data sets that will be modeled by those pipelines, including the combination of probes and perhaps new probes that relate to galaxy evolution that can allow us to constrain the astrophysical components of our models. And from that, we will learn about dark energy, but not only, because we'll also learn about inflation, the alignments of galaxies and their evolution, and the role of baryons in the universe. And with that, I'll just leave it there. Thank you.